All right, so today we're going to tackle the first of, I don't know, many gas laws. It's Boyles Law. Pressure and volume, if temperature remains the same. Who first conducted experiments with gases? That would be Roberto Boyle, an English dude. What did he work with? He worked with a J-tube, mercury, and a staircase. Okay, so you've heard of mercury. You've seen staircases. What is a J-tube again? I think I refer to them as an open-air manometer, where you have a gas that has been captured, and then the mercury is preventing that gas from escaping. He could actually change the pressure on this gas by adding more mercury. So if he added this much mercury, that's how much more pressure was added. He collected very, very precise data, and this is what he discovered. When he had 29.10 inches of mercury, the volume was 48. Oh, okay. Increased the mercury, 40. Increased. So as you are increasing the amount of mercury, what's happening to the volume? Going down. Okay, not only that, but when he multiplied these two numbers, you got numbers that are all over the place, but if you consider sig digs, what did he find? The same number. That meant something, math dudes. What did that mean? Do you see the relationship? Here? Was what? Okay. But basically, as he increased the pressure, what happened to the volume? By how much? The only thing you could say about this, because it always multiplied into the same number, was if you increased it by pressure X, then the volume would have to decrease by volume X. Whatever you did to the pressure, you did the opposite. That's the only way that you could undo the damage. You saw that? As you multiplied the numbers, one number would have gone up, but the other one was going down by the same amount, which meant everything got equaled out. Wow, he had found the relationship. So what can we deduce from the data? Who can put it all together? Raise your hand. Somebody besides Tier. What is the relationship between pressure and volume? Yes? By the same amount. That's right. Or vice versa, right? As pressure goes up, volume goes down. As pressure goes down, volume goes up by the same amount. By the same amount. So what happens if you double the pressure? What happens to the volume? Elizabeth? By? Which is? Yes, you half the volume. Simple. So, when he graphed it, he got a beautiful, what do we call this in math? An arc? No. What kind of relationship is this? Inversely proportional. Inversely proportional. You didn't learn this in Algebra 2? Okay, so if the pressure is going down by 1 and you have a volume of 1, what happens if the pressure goes down by 2? Pressing, the volume goes, if the pressure goes up by 2, the volume goes down by 2. Huh? Does that make sense? Okay, because remember, whatever you're doing to the pressure, you're doing the opposite to the volume. goes down by 2, the volume must divide by 2.
I was looking at the disc and I had like down, like
The disc is putting pressure on the volume. So, right, did you notice that it cut it in half? So if you go down by 4 times, then you will have a quarter the volume. What do we call this relationship again, Southmaid? Mathematical relationship? Inversely proportional. Inverse proportion. Okay, so what did he discover? That whenever you have a pressure and you multiply it by volume, it always equals the same number. If temperature is constant. Okay? So if we know a gas pressure and volume, and we then change one of the variables, can we determine how the other variable was changed? Actually, yes. Let's do it. Let's say the beginning conditions is conditions 1. P times V has to equal what? By the way, the reason why it's K is because the Germans have the word constant, right? Constant. What? So how do the word constant begins in German with the letter K? And what was before, now English is the international science language. But back before in 1950s, guess what was the international science language? German. German. Okay? So, K stands for constant. You got to say it with Fleming. Constant. Because it's German. All right? How about conditions 2? The conditions after something changes. What does P times V equal now? Okay. So if they both equal each other, we can set them equal to each other. And this is Boyles Law if temperature is constant. If temperature changes as well, we'll have to use a different law. All right? Yes?
Does that only for, does K vary by element?
No.
It doesn't matter.
It doesn't matter. Okay, keep in mind that we're talking about gases. They're far away from each other. They're individual agents. We say that they don't interact with each other. So it doesn't matter whether you are gassy Elias or gassy Ma or gassy Tier. Okay, you guys are going to act the same. You're gases. Now you're going to weigh differently, but you're going to act the same. Because, yeah, basically all gases have the same density. All right, Freon 12, the common name for the compound CCl2F2, was widely used in refrigeration systems, but has now been replaced by other compounds that do not lead to the breakdown of the protective ozone in the upper atmosphere. Basically, if you ever watched Snoopy, Charlie Brown, what was that? That was the teacher going, this is just stuff for you to read before you get to the real stuff. Consider a 1.5 liter sample. What's that? Pressure or volume? Of gaseous CCl2F2 at a pressure of? If the pressure is changed to at constant temperature, so that allows us to use Boyles Law, will the volume of the gas increase or decrease? All right, let's get down what we have. V1 is 1.5 liters. The hardest part about these things is making sure that you connect the ones together. Make sure you know which one is partnered up with which one. You have two pressures, but read it carefully. Which pressure should we partner up with V1? Consider a 1.5 1.5 liter sample at, okay, so this one is connected to this one. And then the volume is changed because the pressure goes to 150 torr. Best thing you can do is just read it, think it through. Ah, Corinne, what are you doing to the pressure? Up or down? By how much? Estimate. No, by what factor, my dear? 150 divided by 50 is what? 3, yeah. Okay, so it goes up by 3 times. So what should we expect the volume to do? Go down or up? Down by 3. So it's at 1.5 liters. Estimate. The answer should be around 0.5. Very good. All right, let's do it. 1.5 liters times 0.56 torrs equals X times 150 torr. X is equal to? No. Did you say 84?
Oh, I said
0.56.
0.8.
No, it's
Oh, I saw the
0.56.
first equation.
0.56. Is that around 0.5? Yes. That's just a way of checking, making sure that you're doing it right. Because you know the calculator is run by GIGO, right? What does GIGO stand for? Yes, Dane. No. Garbage in, garbage out. So if you put it in wrong, it's going to come out wrong. It's not the calculator's fault, it's your fault. That's why if you think it through first, you'll have an idea of what the answer should be, and that makes things easier. Yes? 1.5 by 0.56 and then divide by 1.50 or 150, I'm sorry.
Oh, it's 56 on that one.
Oh, sorry.
Also, 1.5 times 100 equals 150. So if you divide 56 by 100,
Mwah, 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 0.725 liters. After the piston moves up to a volume of 0.075 liters, the fuel air mix initially, so what should we link 1 atmosphere with? Calculate the pressure of the compressed fuel air mix, assuming both temperature and amount of gas remains the same. Okay, so Maddie, estimate volume going up or down? By a factor of? Okay. Divide 0.07 into 0.7. No, come on! By a factor of what, guys? 10. So if this goes down by 10, what must happen to the pressure? So what would we expect the answer to be around? Let's do it. 0.725 times 0.0 times 1 atmosphere equals 0.075 liters times X.
It's
9.67 sig digs, 2 sig digs, so it's 9.7, correct? Okay. Is that around 10? We did it. Yes?
So do you always have to like find where it's going, like you have to find 10 and stuff?
Yep. Easy peasy